In this assignment, we will write code to control the movement of the enemy. The enemy will be driven by the animator, taking movement from the root motion of the animation clips that we provided previously. Animator parameters control which animation states the animator should play, and therefore how the enemies move. We will set these parameters using velocities from the Nav Mesh Agent, and we will modify the values with code to correct certain behaviors. When using the Nav Mesh, the system gives the agent a desired velocity. This is not the actual velocity that the agent is moving, but one that it should head towards. Nav Mesh agents such as our enemy have a waypoint path to a destination, shown here by a red line. The agent turns to face the waypoint whilst travelling towards it, and we say that the velocity of the agent, shown by the black arrow, is heading towards the desired velocity, shown with the green arrow. This desired velocity will be the basis of the values that we'll send to the enemy's animator parameters speed and angular speed. Let's begin by creating the script to control these parameters. Add a new script to the robot guard called enemy animation. Select char robot guard and choose add component, new script, and name it enemy animation. Launch the script for editing and prepare it. First, let's take a look at the class variables that we will need. There is only one public variable that we will need, which is a float we will call deadzone. The deadzone, similar to a deadzone in input terms, is a value range which should be ignored. In the case of enemy navigation, we do not want the enemies to attempt to turn when the difference between their forward direction and the desired velocity is very small, and we define this with the deadzone. Without this, we would see the enemies oversteering and walking in wavering lines towards each waypoint, as shown in this example. We will need 6 private variables, the first of which is a reference to the player's transform. We will need this to set the direction that the enemy faces to the player when they are in sight. Next, we will need a reference to the enemy sight script so that we can change the animation based on whether the player is in sight or not. Then we will need a reference to the Nav Mesh Agent component which will be guiding the enemy's movement. Next, we will need a reference to the animator component, and to help reference its parameters, we will need a reference to the #ID script. The last will be an instance of the helper class that we made during the last assignment, animator setup. Next, we will use the awake function to set up these references. In addition to allocating the references, we will also need the awake function to perform a number of other actions. Firstly, we must make sure that the rotation of the enemy is set by the animator and not by the Nav Mesh Agent. This will reduce the appearance of foot slipping whilst turning corners. We will also need to create an instance of our helper function from the previous assignment, and in doing so, call its constructor. We can pass in the animator component and the #ID script that we already have a reference to. We need to set the layer weight of the different layers of the animator. The weight value controls the balance of animation from the layers on the animator. We are going to make both the shooting and gun layers have a weight of 1, meaning that they will totally override the layers beneath them, such as the base layer. This means that the animation would be purely based on those layers. However, we are using a mask for both the shooting and gun layers, so that the only parts of the body they can override are the upper body and right hand respectively. So we use the setLayerWeight function and use the integer of the layer. For example, the base layer should be referenced with a 0, so because we're referencing shooting and gun, we will use 1 to represent shooting and 2 to represent gun, and we set both of them to 1f. The last thing that we need to do in the awake function is to convert the deadzone variable from degrees to radians. This is because the animator controller we made earlier measures the parameter in radians. Luckily, the mathf class has a constant that we can use for this, deg2rad. A constant is like a variable. However, once it has been set, it cannot be changed. In order to convert a number from degrees to radians, we simply multiply by this constant. The majority of this script will be setting up the animations based on the Nav Mesh Agent. To do this, we will create a function that we can call in the update function. We will call it nav_anim_setup. The first thing we are going to do in this function is to create two floats for the speed and angle parameters that we will pass to the helper class's setup function. Now we need to decide if the player is in sight. If the player is in sight, then we want the enemy to stop, so we will set the speed parameter to 0. Now we need to find the angle between the direction the enemy should face and the direction it is actually facing, negative to the left and positive to the right. We will need to make another function in order to do this for us. It needs to return a float, and we'll need 3 vector 3's as parameters: a vector we are measuring from, a vector we are measuring to, and another vector to determine which way is up. We will call this function findAngle. The to vector we are going to pass into this is the Nav Mesh Agent's desired velocity. This will sometimes equal 0. If this is the case, then it might cause an error, so we will need to put in a way to check for this. If the desired velocity is 0, then we want the direction to be 0. If this is the case, we can simply return 0 from the function, and if this isn't the case, then we will continue with the rest of the code. The next step is to find out the absolute value of the angle. We can do this very simply with the vector3.angle function. Now we need to determine whether this angle is to the left or to the right of the forward direction. To do this, we can find the cross product of the two vectors and check the resultant normal vector. Using the left-hand rule for the cross product, we know that if the to vector is to the right of the from vector, their normal will point upwards. See the lesson on vector maths linked below if you need reminding of this. Now we can find the dot product of this normal and the up vector that we passed in. If the normal and the up vector are pointing in the same direction, the result will be greater than 0. Therefore, we can multiply the angle that we've already calculated by the sign of the dot product that we have found. This will show whether the desired velocity is to the left or the right of the forward vector. Remember that we need this angle to be in radians, so we need to multiply it by the deg2rad constant that we used earlier. And finally, we can return the angle. Now that we have a function to find the angle, we can use it in our nav_anim_setup function. The from vector is the enemy's forward vector, the to vector is the vector from the enemy to the player, and we will use the enemy's up vector as the up vector. Now we need to account for when the player is not in sight. Given that the player is not in sight, we want the speed to be based on the Nav Mesh Agent's desired velocity. To achieve this, we can use projection, in order to project the desired velocity vector onto the enemy's forward vector. Projection allows us to take two vectors and find out how much of the first vector is in the direction of the other vector. A projection is found by drawing a line from the tip of the first vector towards the second vector. It must be drawn so that this line is perpendicular to the direction of the second vector. The point of the intersection of this line defines the end of the projection vector. Since we're projecting the Nav Mesh Agent's desired velocity onto the enemy's forward vector, the resultant vector will be small if the enemy is not facing the same direction as the desired velocity. The speed variable will be set to the magnitude of the projection vector. Without using this projection, the enemy might have a high speed whilst facing the wrong direction, and thus run in a wide arc in order to face the correct direction. Next, we need to determine the angle. Again, we will use our findAngle function, but this time the to vector is the Nav Mesh Agent's desired velocity. Since we are using damping to set the animator parameters when they are turning, They won't stop turning as soon as they face their correct direction. Instead, they will continue to turn very slightly. They will then need to turn back to compensate. This will result in a snaking motion as they finish turning corners. In order to prevent this, we need to put a check into our function. This check will simply be whether the angle is small, i.e. less than our dead zone variable. If it is, then we avoid using the animator controller to set the direction that the enemy is facing. To do this, we set the angle to 0 and set the enemy's transform to look at the desired velocity from its own position. Now that we have calculated the speed and angle, we can pass them into the setup function of our helper class animator setup. They can then have damping applied and be passed into the animator controller. Now that we have our completed nav anim setup function, we can call it in the update function. Note that whilst we have inserted this function above ones that we have already written, this is not necessary. We are doing this in order to maintain a flowing structure to the script. First come the class variables, then the awake function is called, then every frame the update function is called. This in turn calls the nav anim setup function, which calls the find angle function. The last thing we need to do with this script is to affect the root motion of the enemy. Normally we have the choice of either applying root motion or not on the animator component. However, if we use the onAnimatorMove function, which is called after update every frame, then we can affect the root motion manually. There are two things we need to control in this function: the velocity of the enemy and its rotation. To control the velocity, we must set the Nav Mesh Agent's velocity to the delta position of the animation divided by the delta time. This is the change in position per frame. As for the rotation, we have already set the Nav Mesh Agent so that it does not control rotation. This is so that we can affect the rotation directly using the animation's root rotation. And that's our script complete. Now that the script is finished, we can save it and return to the editor. Don't forget to tidy the script away by putting it into the enemy folder. Expand the scripts folder and drop it from the root of assets into the enemy folder. Now let's save the scene and save the project. In the next assignment, we will be making a script to make the enemy shoot the player.